Okay, hello everyone. So it's a pleasure to have with us today Sourav Chatterjee from Stanford, who will tell us about his work on young meals. So
Okay.
please.
Yeah, you're saying something. Yeah. Can I start?
Yes, yes.
Okay. Okay. Thanks, Omar, for the introduction, and thanks, Jonathan, for the invitation. So it's a real pleasure, and 90 minutes is really perfect for this. So, but I'll not go on for 90 minutes. Let's see how long it is. So this is some work on three-dimensional Yang mills that I'm currently doing with my wonderful student Sky Cow, who I think is also here. And so if you have questions, you can either ask me or you can ask Sky on the chat. You unmute yourself and ask me directly, or you can ask Sky also. And this is still ongoing, so it's not finished. And so I'll tell you only the results that we have finished proving, and there may be more things coming. So let's begin right from the beginning. So I'll assume zero knowledge about Yang mills. So that's where I start with, but some knowledge of probability, since this is a probability seminar. So let's see. Okay. So to understand the origin of Yang mill theory, so let's start with Maxwell's equations of electromagnetism in the absence of electric charges or currents. So these are the equations governing the evolution of an electric field interacting with a magnetic field. So what's an electric field? It's a three vector at each point of space and time. So it's three vector at each point of space that's evolving in time. And the magnetic field similarly is also three vector. And Maxwell in the late 19th century discovered that the evolution in the absence of electric charges or currents, the evolution is governed by these four equations. Okay, these are Maxwell's equations of motion. Okay. Now, so they look kind of strange. So let's put it in a different framework. So instead of the electric field and the magnetic field, consider a single field on space-time. So now you have a four vector at each point in space that's evolving in time. So you have and each vector. So these AIs are not real numbers. These are imaginary numbers. So anyway, it's the same thing. So you have these imaginary numbers, and this field A is known as a gauge field. Now, the gauge field defines a 4x4 matrix at each point of space-time as follows. So you have, so the indices run from 0 to 3. Fjk is del ak del xj minus del aj del xk. This derivative, so this defines a 4x4 skew-symmetric matrix at each point of space-time. So this is known as the curvature form of the gauge field. Okay. And given an arbitrary gauge field, suppose you start with the gauge field, you can define two vector fields, electric and magnetic fields as follows, E and B as follows. You take the F matrix and you extract E and B from that. So remember, F is a skew-symmetric matrix, skew-Hermitian matrix. Skew-Hermitian matrix. So basically it has the 6 free entries, and you extract your E1, E2, E3, and B1, B2, B3 from this in this particular way. And note that these are real fields because these are all imaginary numbers. So if you multiply by I, you get real numbers. So it can be easily checked that the above definition of E and B, they automatically ensure the first two of Maxwell's equations are satisfied for any gauge field A. The way this is defined, you can check that the first two equations are automatically satisfied. So this is sometimes called the Bianchi identity in differential geometry. Now, what about the other two equations? So then you define a functional on the space of gauge fields like this. So you take this double sum fjkx squared. So remember, these are imaginary numbers. So the square is a negative number. So you put a minus sign, you get something positive. You sum it up and integrate over R4. And suppose the integral is finite. So note that this is non-negative. And suppose we want to find the local minimizers of this SA. So the local minimizers, finding that is a variational problem. So the fields A that minimize this or locally minimize this. And the Euler-Lagrange equations are the third and fourth Maxwell equations. So that's nice. So you have this sort of arbitrary thing, these equations, they are actually minimizing some kind of action. So So the purpose of the gauge field is the following. So Maxwell's equations a priori look quite strange and arbitrary, and so it was Hermann Weyl, I think, who came up with this gauge theoretic formulation. And this puts Maxwell's equations in the framework of Lagrangian mechanics. So in Lagrangian mechanics, a physical system attains a state that minimizes suitable action. So you define the action over space and over trajectories in space and time. And for the electromagnetic field, the action is given by this function S from this previous slide. Now, you can always ask, is there a one-to-one correspondence between the gauge field A and the pair of electric and magnetic fields that you extract from A? And the answer is no. So there is a whole class of gauge fields corresponding to a single pair. And this is the origin of this gauge equivalence, or gauge invariance. So we'll come back to this later on. And you can actually completely describe the set of all A which correspond to one pair E and B. And this gauge field is not a physical object, it's a conceptual one. So the real thing is this pair E and B. And this equivalence class of all gauge fields corresponding to a single pair is this true physical object. So that's the origin of this gauge theory. That is, you have this conceptual thing, gauge field, called the gauge field, which is not a physical object, but it gives rise to some physical things like this electric and magnetic fields, and these equivalence classes that give rise to a single physical object. These are the main objects of interest. These are the things that you can actually handle with experiments. You can observe in experiments. Okay, so now you generalize that. So earlier we had a field A, which is a map from R4 to the fourth power of the imaginary axis. We can consider a map from R4 into this Gothic G to the fourth, where this G is a Lie algebra of some compact Lie group contained in unitary group for some n. So this A is a map from R4 into G to the 4. And the previous case, the electromagnetism corresponded to G equals E1, for which the Lie algebra was the imaginary axis, I times R. And now when you have a general compact Lie group, you define FJK as follows. There is a commutator term, which was absent because commutator is 0 for abelian fields. So now if you have non-abelian, you have this extra term. And this definition comes from differential geometry. These are called these connections of a principal bundle. And this is the curvature form. This is the curvature form. But I'm just writing everything in coordinates just for convenience. I don't want to get into differential geometric terminology. So F is a 4x4 array of matrices. So now F is again a 4x4 array, but each entry is now a matrix. It's a little matrix. The Yang-Mills action is defined exactly as before. It's FJKX squared. Now you take the trace of that. Instead of just taking the square, you take the trace of the square. And because it's a matrix, and you sum it up, you put a minus. And these are skew Hermitian matrices. Each FJKX is a skew Hermitian matrix. So if you square it again, you get a negative number, take the trace, and so you get something non-negative. So this is called the Yang-Mills action. Okay. So now you have this gauge field, which is each point in R4 is mapped into a 4 tuple of Lie algebra elements. And then you define these FJKs, this curvature form, and you take this integral, and assuming it's finite, it's called the Yang-Mills action. Okay. So where does this come from? So why do we generalize? So we had this nice setting, okay, Maxwell theory and so on. So this is the purpose of generalization. So you have 4 fundamental forces in nature. So you have electromagnetism. These are the interactions between electric fields, magnetic fields, and electric charges. You have weak interactions. These are interactions between subatomic particles that cause radioactive decay. And then you have strong interactions. These are interactions between quarks that hold them together to form protons and neutrons. This is a strong force. And you have gravity. And the standard model is a unification of the first 3 interactions, and it has various other things. So it has matter fields and so on. So, but even without that, just without matter, what you do is you replace U1 by SU3, and you get the equations for the strong force. This is called quantum thermodynamics. And you replace U1 by SU2 cross U1. This gives the equation for the combined theory of electromagnetic and weak interactions. This is electroweak theory. Okay. So this this puts everything in the same framework. Okay. So this is why we generalize to this arbitrary Lie groups, and there are only a few Lie groups that are of interest, but we can always work with an arbitrary Lie group. Okay. So now you have these equations, which are really classical equations, but you want something quantum. So Maxwell's equations is a classical in the sense that they predict a deterministic evolution. The quantum mechanical world is random. So what is quantization? In the Lagrangian formulation of classical physics, we assign an action S gamma to each possible trajectory gamma of a classical system. The system follows this trajectory, the trajectory that minimizes the action. So this gives you Newton's equations of motion. In path integral quantization, what you do is, very roughly speaking, you put a complex measure with density proportional to e to the minus I over Planck's constant times S gamma on the space of trajectories, where h is, this is Planck's constant, I squared of -1. So you put something like that on the space of trajectories. And as Planck's constant goes to 0, which is this classical or semi-classical limit, the measure is supposed to concentrate near this action minimizing trajectory due to cancellations caused by rapid oscillations away from the minimizer. So this is extremely difficult to make rigorous in most cases of interest. But this is roughly the idea behind this path integral quantization. Okay. So then how do you handle this, or how do physicists handle this? So what they do is that they remove the I in the exponent. So this gives you a probability measure, which looks more manageable mathematically. That is, you don't have to worry about cancellations. These are known as Euclidean field theories. And often physicists consider it enough to study these Euclidean field theories because the results they get transferred to quantum theories by analytic continuation. And again, all of this is very difficult to make precise. So Euclidean field theories are natural objects for us, for probabilists, and so we'll just be happy to study these, leaving aside the quantum versions for now. Okay. Although there is a big machine in constructive field theory which takes these Euclidean theories and they produce the quantum theories out of that. So I'm not going to talk about that, but there is a machine to do that. Okay. So Euclidean Yang-Mills theories. Recall? G is a compact Lie group containing UN for some n, and this Gothic G is a Lie algebra. Let script A be the space of G connections on R4, namely the set of all maps R4 to G to the 4. And so it's not really all maps, it's maps of a certain regularity. We'll specify that later on. Depends on the purpose, but and then you define the curvature form and the Yang-Mills action as before. And heuristically, a Euclidean Yang-Mills theory in R4 is a probability measure on this space of connections with density proportional to e to the minus beta times the Yang-Mills action at A with respect to some hypothetical Lebesgue measure on this space of connections. And beta is a coupling parameter, so it's typically it's 1 over G squared, where G is the coupling strength. But anyway, we'll just say that it's a positive parameter. And this hypothetical object is sometimes called the Yang-Mills measure in the probability literature. And the construction of this measure is a key step to the solution of the Yang-Mills existence problem, which is still open. It's one of the 7 Clay Prize problems. And there is a lot to do. Once you construct the measure, you have to prove it has various properties so that you can actually construct the quantum theory out of that. And so there are a lot of steps after that. But this is the first step. Well, maybe I should say the first step, not the key step. Okay, so this is the thing. So you have these space of all maps, and then you put some kind of Lebesgue measure on that, and then you have to put density in front of that e to the minus the Yang-Mills action and make sense of this thing. Okay, so I should say a few more things before that. So I told you for Maxwell theory, you had these equivalence classes. So these gauge fields are not the physical objects. So you don't want to define a probability measure in the space script A, the space of all gauge fields. You really want to do it on the space of the real physical objects. So these equivalence classes. So I'm going to describe this now. So a gauge transform. So take any A in the script A. All 4 tuples of Lie algebra elements at each point in R4. So gauge field, and any differentiable map G from R4 into the group itself, and define a gauge transform as follows. You start with this field A, and you produce a new field A to the G as follows. A to the G, the jth component of that at a point X is Gx inverse AJX Gx plus Gx inverse del G del Xj. Okay, so del G del Xj is just coordinate-wise differentiation. You think of this G as a subset of UN for some n. And this turns out, this G inverse del G del X is basically del X of log G, okay? And log G is an element of the Lie algebra. So this is an element of the Lie algebra, okay? And this new field is a gauge transform of A. And each choice of G induces a gauge transform. Okay, so again, I'll talk about the exact regularity later on. But each choice of G induces a gauge transform. And in fact, you can show that if you apply G inverse to AG, you get back A. So this actually is a group action. So this set of all gauge transforms is a group, and this A going to AG is a group action. Now, the space of G connections is not physically relevant, this quotient space. So let script G be the set of gauge transforms. Did I write that somewhere? Maybe not. So the script G is a set of gauge transforms. Oh, yeah. And the quotient space of that, A mod script G. So you define two connections to be equivalent if one is a gauge transform of the other. So for example, in Maxwell theory, two gauge equivalent connections give the same electric and magnetic fields. And so this gives the exact description of that. What are these gauge transforms for Maxwell theory? And in Maxwell theory, since it's it's commutative, this G inverse cancels with G, and you only have this extra term out here. So that gives a complete description of this all gauge transforms for Maxwell theory. But in general, for any theory, you get these equivalence classes, and this is this quotient space. And this is one of the big problems in Yang-Mills theory, that the script A is a nice vector space, but this quotient space is very nonlinear. So that's one of the issues, that how do you deal with this quotient space? Okay, any questions until now?
Is there a description of the quotient space?
This is as much as you have. So you say that these are the gauge transforms.
That's a description, but that's
yeah,
not giving coordinates or.
Yeah, no, it's not. Yeah, and there are all kinds of issues. So there are some theorems. So there's this thing called Gribov ambiguity, I know in physics, which says that you cannot really pick a section smoothly. And well, there is this notion of gauge fixing. There are various ways of choosing an element from each class. So there are ways of doing that, and various ways of gauge fixing. There are all kinds of gauge fixing things. So that's as much as we have. So so function f on this script A is called gauge invariant if fa equals fa prime whenever a and a prime are gauge equivalent. For example, it's not difficult to check that the Yang-Mills action, it's gauge invariant. So it's one of the gauge invariant functions. And if you have a gauge invariant function, obviously it can be defined on the equivalence classes, because it's constant on the equivalence classes. So as I explained before, any physical observable must be gauge invariant. So for example, in Maxwell theory, if a quantity is not gauge invariant, it cannot be expressed as a function of electric and magnetic fields, which is what you want. And the most important gauge invariant observables, perhaps, are the Wilson loop observables. So I'll define these later on. And for these reasons, any candidate for Yang-Mills measure must be gauge invariant. So the measure should actually define in this quotient space instead of the space of connections. Okay, so that's one of the things that you have to do. And in any case, it's very hard to define these measures on the space of connections itself. It's too large. So if you want to define anything meaningfully, somehow it has to be on this quotient space. Okay, so let me now summarize the progress that has been made so far. So one common theme in the literature is to look at the problem in dimensions 2 and 3 instead of 4, so that where it's supposed to be easier or more manageable. So all that we've discussed until now have analogs in dimensions 2 and 3. Okay, so this question makes sense in these dimensions. It's not completely physically relevant, although there are some models which, some physical models where you restrict electrons to a sheet and then it becomes a three-dimensional problem, because then time is one dimension and the sheet is 2 dimensions. But mostly, it's not so relevant. But it's good. It's a good start. The greatest amount of progress has been made in 2D. So in fact, we now know more or less how to construct Yang-Mills measure in 2 dimensions. On the other hand, very few results are known in 3 dimensions and 4 dimensions. And many of the above results, also the ones that are available, are for compact manifolds such as tori. And in this talk, we'll be working on the 3D torus instead of the full space. And in the next few slides, I'll talk about some of the known results and present some new ones. So progress in 2D. So there have been many people who have contributed, and this is an incomplete list. So you can see that people have made contributions throughout the last 40 years, all the way up to 2020. And in one of the most recent papers of Chevyev, so Chevyev constructs a space of connections and a probability measure on the space of connections that can be interpreted as a 2D Yang-Mills measure. So previous works on 2D Yang-Mills measure constructed these measures on spaces of observables. So this is, I think, the first one that constructed just on a space of random, actually distributional connection. So this is h to the negative something. And there is also this more recent one by Chandra, Chevyev, Hara, and Shen. They construct a state space and a Markov process on the state space such that the unique invariant measure of this process can be interpreted as a 2D Yang-Mills measure. So there is this approach of Parisi and Wu from the 80s called stochastic quantization, which tries to define the measure by defining a stochastic process, which gives the Langevin dynamics for that. And you say that the invariant measure hypothetically is the invariant So it's not known whether the unique invariant measure exists for this process. It's not clear, but they construct this Markov process on the state space using regularity structures. And they mention in the paper that they have some forthcoming results in 3D, but I don't know what those are. So constructions for 3D U1 theory and 4D U1 theory were given by Gross in 83 and Driver 89. And beyond this, in 3D and 4D, for a general non-abelian Lie group consists of these results of Balaban, many papers from between 83 and 89, and Federbush and this other paper. And so, so there are a whole bunch of all these papers, but as far as we understand, these papers don't really construct the Yang-Mills measure in the way that was done for the 2D case. And in particular, they don't construct probability measures on the space of connections or gauge orbits or observables. Okay. So this is one thing that we would like to do, just as in 2D, we construct a probability measure. So in 3D, we would also like to do that. Now, but there is a basic difficulty, which I'm going to tell you now. So the 2D Yang-Mills measure are constructed on space of distributional connections with enough regularity to define Wilson loop observables, okay, which I'm going to define soon. So heuristically, this is expected to be impossible in dimensions 3 and higher. So there are reasons to believe that this is not possible in dimensions 3 and higher. And the heuristic is essentially that these fields should have the same kind of regularity as a Gaussian free field. And for a Gaussian free field dimensions 3 and higher, you cannot define a Wilson loop observable. That's not defined. And so consequently, so these things are defined through these Wilson loop observables, these Yang-Mills measures. So it's not even clear what the state space should be. So that's the first thing. If you want to define a measure, you want to know what should be the state space. And it's not even clear what's the state space for a 3D or higher dimensional Yang-Mills measure. It should be a space of distributional gauge orbits. So we had these gauge orbits, elements of A/G that I showed, but those will not be enough. So those are sort of like functions, and then you have some distributional equivalent of that, but we don't know what that means. What is the distributional gauge orbit? To solve this problem, Charalambous and Gross in 2013 initiated a program for constructing this Yang-Mills measure for gauge theories on compact 3D manifolds using connections regularized by the Yang-Mills heat flow. So I'll define this shortly. And so this thing that we are writing, so hopefully will soon be an archive, takes this program forward. So this paper is actually originally posted in 2010, came out in 2013, so it's about 10 years old. So in the remainder of this talk, I'll explain this, what is going on here, what's the main idea, and what is going on, and what is the progress that we have made. Okay. Any questions? Okay. So what are the results? So very vaguely, I'll tell you, and then I'll go into the details. So our main contribution is the definition of the state space for Yang-Mills measure on the 3D torus as an abstract space of distributional gauge orbits. and a criterion for tightness of probability measures on this space, so that if you have a sequence of approximating measures, you can verify that they are tight and there is a convergence subsequence. So we have shown that this tightness criterion is satisfied by sequences of probability measures approximating U1 theory, as well as regularized versions of non-abelian theories, which allow us to construct these theories. And we expect that this criterion is also satisfied for non-abelian theories without regularization. So there are indications of that. So this is what we're working on. But we also have a more abstract space with a smaller class of observables where we are able to construct 3D non-abelian theories with no regularization. And I'll tell you what are the difference and why we are not satisfied solely with this and we want this nicer thing. So I'll go into all that. And let's talk about this abstract construction first, since this is simpler. Okay, so this is what I'll talk about first, and then I'll tell you what is the main obstacle and so on. Okay, so first let's start with the Wilson loop observable. So let's define Wilson loop observable. So let A be a smooth G connection from 3D torus T3, which means that it's a map from T3 into 3 tuples of Lie algebra elements of G, and it's smooth, so it varies smoothly, C infinity. So given a piecewise C1 closed path, and we are assuming in the definition of piecewise C1, we're putting that it's rectifiable, closed path L from 0, 1 to T3, let H be a solution of this ODE. Okay, so H is a group valued function, and H prime T is HT times this sum. H0 is started with identity, so it's like an exponential. And from standard ODE theory, given the smoothness of A, this H exists and is unique. And this group element H1 is called the holonomy of A around this loop. And it does not depend on how the loop is parametrized. Okay. Okay. So just a minute, I have to open the door for someone and come back in 1 minute. Sorry. Oops. Okay. Okay, so this the holonomy is sometimes known as the path-ordered integral. So you see, if these were real numbers instead of matrices, this would H would just be an exponential, integral of an exponential of an integral. But these are matrices, and they define what is known as a path-ordered integral, okay, of AJ summation AJ dxj. And this is the formal definition of the path-ordered integral. There are other ways you can define it. Now, let L be a piecewise C1 closed path, and let chi be a character of G. And then take any smooth G connection. The Wilson loop observable WL chi of A is defined as you apply chi to this path-ordered integral. Okay, so this is just chi is any character of G. And these Wilson loop observables have this nice property of being gauge invariant. So if you do a gauge transform to A, you can show that the Wilson loop observable is not going to change, okay, for any smooth gauge transform. So this is all smooth now. So this can be defined on this quotient space. Well, I haven't defined the exact regularity of script T and script G, but anyway. So this is the idea that it can be defined on this quotient space. Okay. So that's the first thing, the Wilson loop observables. The next thing that I haven't defined but I've talked about is the Yang-Mills heat flow. So given a G connection A on the 3D torus, recall that the curvature form is defined as follows. So this is the curvature form. The Yang-Mills heat equation is the nonlinear PDE which defines the evolution of a time-varying connection AT. So del AJ del T is minus summation k equals 1 to 3. So this is all in 3 dimensions. So in 4 dimensions, there'll be sum of from 1 to 4 or 0 to 3. Del fjk del xk. So fjk is this thing, this nonlinear thing here, plus minus this sum of commutators. Okay. So as you see that if you're working with an abelian group, then these commutators are absent, but in general they are there, and it's quite nonlinear because these fjk's have these commutators here, and then there's also this commutator. So it's basically a cubic kind of thing on this side. So this is this strange looking thing. This is actually the gradient flow for the Yang-Mills action. So if you take the Yang-Mills action and you want to flow in the direction where it's decreasing most sharply, okay, so this is how you should flow. This is the gradient flow for the Yang-Mills action. So just as the ordinary heat equation is a gradient flow for the Dirichlet energy, so integral gradient f squared. So if you want to go the sharpest, steepest descent, you get the heat equation. This is similar. So it was shown by Roder in 1992 that for a 3D manifold without boundaries, such as the torus, that's what you're working on, the Yang-Mills heat equation has a unique solution over all time when the initial connection is in H1. So if you start with something in H1, you can define this over all time. Okay, there's a global existence and uniqueness and various nice properties. So it's continuous and so on. So it's all kinds of nice things, but this was first proved in this paper. Now, why do we work with the Yang-Mills heat flow? The main idea behind the Yang-Mills heat flow is that it smooths the connections just as ordinary heat flow smooths functions. And the additional property of the Yang-Mills heat flow that makes it very well suited for gauge theory is that if you start with the initial condition that B0 is some gauge transform of A0, and you make both of them flow according to the Yang-Mills heat flow, then this property is preserved for all time. So BT is AT with gauge transform G for all T. Okay. So therefore, the Yang-Mills heat flow can be lifted to this flow on the quotient space. So you can have elements of the quotient space flowing according to the Yang-Mills heat flow. So physicists have taken advantage of this to introduce this idea of regularizing gauge connections by the Yang-Mills heat flow. These are the two papers where they were introduced. And this has become very popular. So these papers, this one I think has more than 700 citations right now. So many people are working with this Yang-Mills heat flow in regularizing things. And not only for these connections, they thought they do the same thing for lattice gauge theories in discrete setting also. Okay. So now let me go a little bit deeper into the smoothing property of the Yang-Mills heat flow. The Yang-Mills heat flow does not smooth the connection in a direct way. So for example, if A0 is a H1 connection, it does not mean that AT is in a smoother class. It does not necessarily mean. So what does it mean that it smooths? So it smooths in the following indirect way. So at various points of time in the 80s, Zwanziger, Dieterk, Donaldson, and Sarun, they discovered this variant of the Yang-Mills heat flow, which has nicer properties. So there's a different equation. So I'm not writing down the equation. It's a completely different equation. But what it does is the following. So first of all, that equation is more like the heat equation. The Yang-Mills heat flow does, is not. It does not have this nice features that the ordinary heat flow has, and this different equation has much nicer features. Now, what is its relation? So if CT is an evolution according to this ZDDS equation, and AT is a solution of the Yang-Mills heat equation, the same initial data, then in principle, so this is not so easy to make rigorous, but in principle, CT should be a gauge transform of AT for a time varying gauge transform for all T. So you can show this that this new equation is evolving differently, but on the quotient space, it's the same evolution. Okay, so that's the thing. On the quotient space, it's exactly the same evolution. So this was made precise by Charalambous and Gross if A0 is in H1 on compact 3 manifold. So this is the thing that was, at least for small enough time, this was made precise by Charalambous and Gross. And moreover, they showed that CT is a smooth. So this CT is evolving very nicely. If you start with H1, in an infinitesimal amount of time, for any small positive t, the CT becomes a C infinity connection with all kinds of nice bounds and all that. Okay, so this is very good. So this allows us to define regularized Wilson loop observables, which physicists have been using, but it gives a mathematical definition of that. So the smoothing property allows us to define regularized Wilson loop observables WL chi T of A. So remember, L is a loop, chi is a character, and T is a positive time for any A in H1 by letting by defining it as like this. So you start with A, you let it flow for a little bit of time T, and then there is a gauge transform. Then by this result of Charalambous and Gross combined with Roder's global existence theorem, that after any time T, you'll be able to find a gauge transform so that when you apply the gauge transform, you get a smooth connection. And then you can define the Wheeler-Wilson observable. Okay? So for the smooth connection, you can define it. And then you can show that it's well defined. So it doesn't matter which gauge transform you choose, or so it doesn't really matter. But then you can define for any H1 connection, you can define a regularized Wilson loop observable. So just like the usual observables, the regularized observable is also gauge invariant. So you can show that if you take A and you take A to the G, for any gauge transform sufficient regularity, you get the same observable. So the regularized observables are also defined in the quotient space. Okay. So everyone with me, any questions until now?
Yeah. Excuse me. So what was the point of the previous heat flow then? I mean, if it's not smoothing the
the Yang-Mills heat flow, the Yang-Mills heat flow, it exists globally. So for the ZDDS flow, you don't even know it exists globally. So it exists only for small. So Charalamus and Gross showed it exists for small amounts of time. So what you do here is that you take the ordinary flow, the usual Yang-Mills heat flow for a sufficient amount of time. So you have a target time T. You go up to very close to T, and then you do the ZDDS flow a little bit.
I see. Thanks.
And that's how you can define. So the ZDDS flow is not even defined. It's not been proved that it's globally existent.
Thank you.
Because Rodin's theorem is quite hard. The global existence theorem. It's a hard result. Okay. So this regularized Wilson loop observable can be defined on this quotient space. So now let me define what is the exact quotient space. So henceforth, let script A be the set of all H1 connections on T3. That's script A. Okay, we'll work with H1. And there's a reason for that. I'll come to that later. Script G is a space of all continuous maps from T3 to G, so that G inverse DG is in H1. So DG is the weak derivative of G, and G inverse DG is in H1. So this G, you can show it's a group of gauge. It's actually a group, and it acts on A. Okay, it sends elements of A to elements of A. So this definition is not ours. This comes from the theory of Uhlenbeck compactness. So this is a standard thing. The quotient space is space of gauge orbits, and we seek to define a Yang-Mills measure on the space or an enlargement of it. So you want to define distributional versions of elements of this quotient space. Okay. So one of the main things is that regularized Wilson loop observables define gauge orbits. So one of the things that we prove in the paper is this. So in what way? So let A1, A2 be in H1 such that all regularized Wilson loop observables are the same for A1 and A2. So for all L, chi, and T, you have this equality. Now, let C1 and C2 be the ZDDS flows with these starting conditions. C1, 0 be A1 and C2, 0 be A2. Then from this first point, we know that WL chi of C1T is WL chi of C2T for all L chi and T. So if you fix a connection, fix a time T, then you have these two connections, C1T and C2T, which have same Wilson loop observables for all loops and all characters. And there's a result of Sengupta from 1994 for smooth connections. It says that under this condition, you can deduce that C1T is C2T to the GT. So one is the gauge transform of the other. And I should say here that this is not for all gauge groups, but it includes everything of interest. So it basically includes SUN, UN, ON, SON, all abelian groups, and all finite products of these groups. So anything that comes up in practice is covered by this result. And this result says that if Wilson loop observables are equal for two smooth connections, then one is a gauge transform of the other. So now you take T to 0. So C1T tends to A1 as T goes to 0. C2T tends to A2 as T goes to 0 in H1, both in H1. So this was proved by Charalamus and Gross. That is, the evolution is continuous. We see in particular that the H1 norm of C2T is uniformly bounded in a neighborhood of 0. And C2T to the GT is C1T. So that is also uniformly bounded. So you have this connection C2T and GT, so that these two both have uniformly bounded H1 norm. And this lemma in the proof of Uhlenbeck's weak compactness theorem, from which you can deduce that under this condition, you can actually say that these GTs, these gauge transforms, have convergent subsequences. So convergent meaning that GT converges in L infinity to G, but not only that, this GT inverse DGT is also converging to G inverse DG through a subsequence in L2 as T goes to 0. So you can extract a convergent subsequence of gauge transforms. And using the above, we showed that this A1 must be A2 to the G for some G. So the main thing is that if you have two H1 connections whose regularized Wilson loop observables are all the same, then one connection must be a gauge transform of the other. Okay. Any questions about this?
So are the Wilson loop, I mean, you're trying to define a measure. Are the Wilson loop variables like moments or something? That is, if you can.
In some sense, they are.
I mean, those are your observables. So you have a class of functions, and if you can say what's the expected value of that class of functions, then you've defined a measure. I mean,
yeah. So
can you do that for a large class of functions?
Yeah, I mean that's the question. I mean, that's what I'm asking: is are the Wilson loop variables sort of substituting for a large class of functions? That's exactly.
That's what they're substituting for a large class of functions. And we will see both, so we'll see these two constructions. So one is easier construction, where if you declare that these regularized Wilson loop observables are the only class of functions that you're essentially interested in, and you can produce other functions from that, then you can have a construction. But then if you insist that you need somehow, maybe you need more, then you have to proceed in a different way. So that's the idea, that these form the interesting. So this is sort of like in Brownian motion, the finite dimensional distributions, that kind of thing. So in that sense, yeah.
The Wilson loops are separating on the quotient space.
Yeah, So the Wilson loops are separating the quotient space, except that if you are in H1 with regularity H1, Wilson loops themselves are not well defined. So you have to work with this regularized Wilson loop. So if you're in 3 dimension and you have H1 connections, then you don't know how to define Wilson loop variables. And so then you do this little bit of regularization, and then you work with that, and then use the scheme to prove that those regularized variables are also separating. Okay, so there is, now you can see this abstract approach, completely, sort of simple thing that you can do is you take, the Wilson loop variable corresponding to chi, to a character chi, has absolute value at most the degree of this character. So you take this disk of radius r, so disk of radius d chi, and you take the product overall L chi and t. And so this is with the product topology, the space is compact. And then you consider the map from the quotient space into this space, which takes an orbit to this tuple of regularized Wilson loop observables. And by the result from the previous slide, this map is injective. Okay, so you can naturally view this quotient space as a subset of this product space. Okay, and then you can take the closure of this. And then this is a compactification of this gauge orbit space. So this is a very simple idea of how to compactify. And then you can construct the measures. So this is the first more abstract compactification. So recall that we want to construct a measure with a probability measure with this formal representation. You have this hypothetical Lebesgue measure on the space of connections, and you have the Yang-Mills action. So e to the minus beta the Yang-Mills action times a normalizing constant, and then you do d mu a. So what do you do? So you take some m and r, and nu mr be the normalized restriction of this measure. So you can define this measure if you restrict yourself to all connections which have Fourier coefficient 0 beyond m, okay? And Fourier coefficients are absolute values bounded by r when n is less than m. So this is perfectly well defined. So there is no problem defining this. So it's discrete approximation. You can do other kinds of discrete approximations using lattice gauge theories. So you can do that and let mu mr be the push forward of this measure onto this compactification. So that I showed in the previous slide. So you first push it forward to the quotient space, and this quotient space is embedded in this compactification. And then just by the usual abstract things, Banach-Alaoglu and Rees representation, you can find subnets along which you can have a limit measure. So you can construct a limit measure via subnets. And any such limit measure is a valid candidate, and we believe that the limit is unique for various reasons. We believe that this is unique, and this gives you construction of the measure, as long as the regularized Wilson loop observables are your only observables of interest, there is nothing wrong in this. So this is just a valid construction. Well, you are implicitly using the action of choice here, but you get a construction like this. Okay. So, but there are some problems with this construction, as I said. So there's some limitations. So since you're working with this product topology, the set of measurable functions is severely limited. So to be more specific, suppose that Q is a random element from this script C, our compactification, that is drawn according to our Yang-Mills measure. Then for any L, chi, and T, there's a well-defined notion of the regularized Wilson observable. So this random variable is well-defined. But suppose we ask, is this continuous in this loop and in time? Okay, so suppose you vary the loop a little, is it continuous? So this event is not even measurable with respect to this sigma algebra. You know, that's one of the big problems, and you want it to be nice and smooth. Is something that is, you know, a reasonable probabilistic object. And this is analogous to the construction of Brownian motion as a random element of R to the 0 infinity. Okay. And this problem is remedied for Brownian motion by showing that it has a continuous modification. So this is what we teach graduate students, that we first construct in R to the 0 infinity. And then one of the constructions is that you do it in 0 infinity, and then you do a continuous modification, and you get a Brownian motion with much nicer properties. So this allows us to construct Brownian motion of space C0 infinity with the topology of local uniform convergence, which has a much richer set of measurable functions, and you can ask for many other things. And the question is, can something similar be done for this Yang-Mills measure that was constructed using this very abstract, relatively simple approach that we did, using this regularized loop, Wilson loop observables? And for example, can we do something where this kind of question can be answered? Okay. So we now embed this quotient space in a different space X, which is actually smaller than our earlier space Y. So here is the space. So this is, let X be the set of all sequences like this, xt, 0 less than t less than infinity, where the very important thing, notice, is that t starts strictly bigger than 0. It's not starting at 0.
But there, show if there are continuous number of, I mean, sequence sounds countable to me, and that looks continuous.
I didn't know what to say. You know, well, it's not a sequence. It's a function from X is a function from 0 infinity to.
Oh, that's okay.
Yeah. So you have xt is in this quotient space, and the property should be that for each 0 less than s less than t, xt is obtained by running the Yang-Mills heat flow for time t minus s starting from xs. Okay. So this is the evolution of the Yang-Mills heat flow with no beginning. Okay. There is no beginning point, but it's an evolution. So all sequences like this. So this is a much nicer space than X, since this xt is a gauge orbit of an H1 connection, and this map is continuous and all that. So this, you can ask, you know, these Wilson regularized variables are all automatically continuous on this space. Okay, so these are much nicer, and then this quotient space is embedded in X in a natural way, because for any element of the quotient space, you can just start from that element and look at the flow for infinite time, and that gives you a natural embedding. But there are elements of X that are not in this quotient space. So here is an analogy. So consider distribution. So if phi is a distribution, we can sometimes have an ordinary heat flow, phi t, with initial condition phi, such that phi t is a smooth function for each t. So the distribution phi can be represented by this whole flow excluding the time point 0. So for example, the Dirac delta at a point is not a function, but if you let it flow according to the heat flow, at each positive time you get a function. Okay, so you get a narrow Gaussian density, and this whole sequence of, or not sequence, okay, the whole collection of densities with no beginning, which are becoming more and more narrow, this represents the Dirac delta. You know, this sequence represents the Dirac delta. So in the same sense, any collection like this, xt, t between 0 and infinity with no beginning, and it's a Yang-Mills heat flow with no beginning, that can represent a gauge orbit, distributional gauge orbit. Okay, in the same sense as this is represented. Okay. So this is our space of that we are considering here.
How do you know it's non-empty? I mean, its definition doesn't seem so crisp to me. I mean,
okay. So definition, it's non-empty because this quotient space is embedded. So if you start with x0, if you start x0 as a h1, H1 connection, then you can obviously define xt as the Yang-Mills heat flow starting from a x0 flowing up to time t.
Yeah.
You see? So by Roder's theorem, those flows exist. Global existence theorem, those flows exist. So yes, I should have written down. So you see, if you take if you take, let's say, x or let's say q, an element q in this quotient space a/g, then qt is defined for every t bigger than 0, and the sequence, or this flow qt that you define t between 0 and infinity is an element of this space script x. So at least a/g is contained in x.
Okay.
You see, so that's the natural embedding of a/g in x. Okay. So just like, just consider the heat equation. So if you represent distributions using the heat equation, so you represent distribution as the heat flow without a beginning, then of course every smooth function is also in there, because then it's just you take the heat flow starting with the smooth function, but you just leave out the beginning. Okay, just
Thank you.
Yeah. So in this way, we're defining distributional gauge orbits. Now consider the H1 topology on this on script A, the weak H1 topology. There is a sequential version of this weak H1 topology, which is so any topology you can have a sequential version of the topology, where we declare a set U open if and only for any A in U and any sequence A n converging to A weakly in H1, A n belongs to U eventually. So you set all sets U which have this property. So this is an enlargement of the original weak topology, a slight enlargement of that. So we'll work with the push forward of the sequential weak topology onto this quotient space. So there's the reason. We want to define the topology on this space script x. We endow x script x with topology generated by these evolution maps, x going to xt from x script x into a/g, where a/g is endowed with the weak topology. Okay, and so this is the topology. So x, this script x. Remember, well, for want of a better word, I'll just say sequences, but just all flows like this, okay, xt t bigger than 0, flowing according to the Yang-Mills heat flow, where the elements xt are in this a/g. So we put topology in a/g, which is the sequential version of the weak H1 topology on A push forward to this a/g. And then you can take the evaluation maps x going to xt, and you have a topology generated by these evaluation maps. So we endow the space x with that. And that is nice enough because, all these evaluation maps will be measurable. They're continuous, in particular, they're measurable. So anything reasonable you would want to know about these xt's, you would be able to get an answer from that. And for that and for more reasons, because if xt is continuous with respect to this weak topology, then if you take a t prime slightly bigger than t, you can get even stronger continuity property under stronger topologies. So here is the subsequential convergence result. Let bold xn be a sequence of script x valued random variables. Okay, so we are trying to construct the Yang-Mills measure on this space script x. So we take a sequence of well-defined random variables which approximate the Yang-Mills measure, and we want to show this. Suppose that for each t, the Yang-Mills action of xn evaluated at t. So remember, xn evaluated at t as an element of the orbit space a/g. The Yang-Mills actions, these are real valued random variables, and suppose they're a tight family of real valued random variables where Sym is a Yang-Mills action. Then the sequence is a weakly convergent subsequence. So there's a subsequence so that the expectation of all bounded continuous functions converge. Okay, so this is one of the main results of the paper until now. So
that's for each t greater than 0, I think you mean, right?
Each t bigger, so for each t bigger than 0, suppose the Yang-Mills action. So the Yang-Mills action completely determines the tightness. So recall that in the definition you have the Yang-Mills heat flow, but some of this Yang-Mills action comes in. The Yang-Mills action, if this applied to these random variables at each time t, gives a tight family, then you can deduce that this is weakly convergent. So just as an illustration, we can construct U1 theory on this space, as well as these regularized versions of non-abelian theories. And this is essentially, it gives the same, the U1 theory gives the same construction as Gross, but on a different space. So Gross constructs an actual, a distribution, a random distribution. And this is a different, it's on a different space, but it's for illustration. Now, we believe that the theorem can be able to, should be able to construct non-abelian theories without the regularization. So this is what we are currently trying to do to prove this. So the whole program, now that we have a well-defined space, to define these approximations to these theories, and to show that this tightness criterion holds, that these Yang-Mills actions are tight, and once that is proved, then this will have a weakly convergent subsequence. Okay. Any questions? So, I'll now just sketch the proof of this result. What goes into the proof of this? So the main step in the proof is to show this, something about this quotient space, that if you have a sequence of this quotient space valid random variables such that the Yang-Mills action is a tight family, Yang-Mills action applied to these random variables is a tight family, then this has a weakly convergent subsequence on this quotient space. So this is the, I'll show this later. So that's the main step in the proof that gives the criterion for tightness for this quotient space valid random variables. Okay, and and the thing is, why aren't we using this to construct our Yang-Mills measure? It's because we don't expect that our random variables will actually be tight on the quotient space. So we have to go to this other space, but this is an intermediate step. That's so how do we use this to prove our result? So what we do is that using this fact and a diagonal argument, we show that under the hypothesis of the theorem, for any T1, T2, Tk positive rationals, this tuple xt1 to xnt1 to xntk converges weakly. There is a subsequence along which this converges weakly for any rationals. Okay, and we also use the fact that xt is a continuous function of xs for any s less than t, which allows us to go from one point to multiple points. And by the continuity of the heat flow, we show that the above statement also holds for any k tuple of positive real numbers. Instead of rationals, we can move to reals. And then we show that these limits are inner regular. And then we use this Kolmogorov-Buchner construction of projective limits. So you have this Kolmogorov consistency theorem, which constructs these measures if you have real valued or vector valued random variables, but these are more abstract random variables. So for this, you need a slight condition, which is this inner regularity. You need this, and then you have this projective limit that you can construct on this space. Okay, so the main thing is this. Once we have this, the rest will follow from that criterion given in the theorem. Okay, so how do you prove this? So we want to show this step. So the main step, as well as inner regularity, are consequences of the following lemma. So the main thing is that the set of all elements of the quotient space with Yang-Mills action bounded by lambda, for any given lambda, is a compact metric space under the sequential weak topology. Okay, so it's a compact metric space. And the compact metric structure allows us to prove a version of Prorov's theorem for the space A/G because the union of these things. So this space is not exactly a Polish space, but it's a countable union of compact metric spaces. So we can prove a version of Prorov's theorem. And it also allows us to prove inner regularity because this is inner regularity is automatically automatic on Polish spaces. So we have this. So this is what we would like to prove. So here is the step. So there are 3 steps, and here's the first step. So this is the theorem I was alluding to earlier. There's a weak compactness theorem of Uhlenbeck, which says that if A1, A2, etc. is a sequence of H1 connections, so that the Yang-Mills action is uniformly bounded, then there is a subsequence A and K and a sequence of gauge transforms, so that if we apply these gauge transforms to these connections, they converge weakly in H1. Okay, so there's weak convergence in H1. So there's weak compactness theorem. So this shows us omega lambda is sequentially pre-compact in the sequential weak topology, weak H1 topology. Okay, that's the first thing that we observe. The second thing is that taking a sequence AN converging to weakly in H1 to A. So H1, so the observation is that H1 embeds compactly in L4 by the Sobolev embedding for 3 manifolds. So Uhlenbeck's theorem is also for 3 manifolds, the version that I stated. So this is also for 3 manifolds. H1 embeds compactly in L4, we get that AN converges to A in L4. And also weak H1 convergence implies that the derivative of AN converges to the derivative of A weakly in L2. Okay. So combining these two, we see that the curvature forms converge weakly in L2, because the curvature form, remember, has these two parts, the derivative part and the commutator part. The convergence of the commutator part comes from this L4 convergence, because you have commutator is two things, so you want them converging in L2, so you need L4. So you have this convergence of the curvature forms in L2, and the L2 norm is weakly lower semi-continuous. From that, you get that the Yang-Mills action of the limit is less than or equal to the limit of the Yang-Mills action, so it's bounded by lambda. This proves that omega lambda is sequentially closed using this Sobolev embedding and this. And combining this with the fact that it's sequentially pre-compact, we get that omega lambda is sequentially compact under the sequential weak topology. So the only thing remaining to prove is the metric structure. So you have this compactness, and then you want the metric structure. So recall this earlier result that the collection of all regularized Wilson loop observables uniquely determines the H1 connection up to gauge transforms. And using the continuity of the heat flow, we can actually show that there's a countable subcollection of regularized Wilson loops, which uniquely determines the H1 connection. So define a map phi, which takes an orbit to a tuple given by this, all the regularized Wilson loop observables in this countable subcollection. The continuity of these maps, which we proved as a consequence of results proved by Chalambous and Gross. So this implies that phi is continuous when this C to the J is given the product topology. And using the sequential compactness of omega lambda, which we proved, we deduce that phi f is closed for any closed f in this, which shows that phi is a homeomorphism between these omega lambda and its image. And since J is countable, C to J is a metric space under the product topology. So this proves that this omega lambda is a metric space. So this proves that omega lambda is a compact metric space. So there are these three ingredients. You have Uhlenbeck compactness, which shows it's sequentially pre-compact, and then you have the Sobolev embedding, which shows it's closed, which means it's sequentially compact, and then you have these Yang-Mills heat flow and the regularized Wilson loop observables, and this uniqueness theorem, which allows us to, together with sequential compactness, it gives a homeomorphism between this quotient space and a subset of a metric space, and shows that this is metrizable. So this proves that it's a compact metric space. Okay, so this is the thing. So to summarize, you show that this omega lambda is a set of all gauge orbits with Yang-Mills action bounded by lambda under the sequential weak topology. So actually that's equivalent to the weak topology if you restrict yourself to that subset. So under the weak H1 topology, these are compact metric spaces, which allows us to, prove the tightness criterion using this. And so we constructed, so here's a summary. So we constructed Yang-Mills measure for the three torus of an abstract space seen in using these regularized Wilson loop observables, taking forward this program initiated by Chalambous and Gross. And this is analogous to the construction of Brownian motion in R to the 0 infinity with similar problems. Okay, so we want something better. And for a better construction, just as Brownian motion on C0 infinity is better than in R0 infinity, we introduce the space of distributional connections represented as trajectories of Yang-Mills heat flow with no beginning. Okay, so you exclude the point 0, and then you have these flows, and we give a sufficient condition for a sequence of probability measures on X to have a subsequential weak limit using this Uhlenbeck compactness and Sobolev embedding, and also this regularized Wilson loop observable. So this whole thing. And we showed as an illustrative example, so I didn't present it here, but it holds, everything goes through for U1 theory and regularized non-abelian theories. So we can do that, this tightness criterion holds, and you get, so you actually need to expand to the bigger space for U1 theory. So that is also necessary, because you will not get a connection as a limit, you will get a Gaussian free field type of object. And we believe that the condition also holds for non-abelian theories without regularization. So we are trying to do that. And so that is all. So, okay, 65 minutes. Okay, thank you.
Let us unmute and thank
Sourav, the statement that SYM of Q is tight. SYM of Q, does that mean evaluation of SYM at x of t for some t's bigger than 0? Okay. So there are two questions. SYM of Q, what does it mean? And also, what does it mean for it to be tight?
Yeah, so, okay, so let's see.
Yeah,
so
that's right.
Yeah, this is good. Okay, so here's a theorem which says that you have a sequence of x valued random variables. X is a sequence. X is the space of all these Yang-Mills closed with no beginning. And I'm saying that SYM. So if you have a sequence of x valued random variables, x SYM of xn of t n greater than or equal to 1 is a tight family of real valued random variables. So these are real valued. So if these are x valued random variables, these are real valued random variables. And so if you have a tight family of real valued random variables for each t, then we show that xn has a weakly convergent subsequence. Okay, so that's the result for script x.
So for each t, the measure on the line induced by that function, that sequence of measures, that's tight.
Yeah, sorry, I presented in this probabilistic way using random variables, but another way to say that is, suppose you have a sequence of measures, probability measures from the space of script x, so that the push forwards of the measures under these two maps. So first you evaluate, you take the evaluation map from script x to a/g by taking x going to xt, that's the evaluation map. Then you compose it with the Yang-Mills action, so that this composition of these two maps push forward the measure to the real line. And then you have a sequence of measures on the real line, and you want that sequence of measures to be tight. And so that is the theorem. And to use that, I'm proving this intermediate lemma, which says that that if you have a sequence of measures on the quotient space, so that if they're pushed forward under the Yang-Mills action of the tight family, then the sequence of measures itself is tight on the quotient space.
That SYM of Q is what you were referring to on the previous slide.
Yes.
For each t greater than 0.
Yeah, each t is strictly bigger than 0.
Yeah.
So here you have composition of two maps. You first take x. You first take the map which evaluates at t. Then you take the Yang-Mills action. So in 2 steps you go to the real line, and here you just go in 1 step to the real line from a/g to the real line. Okay. And then I show that this.
No, wait.
Yeah.
This 1 step means SYM of Qn is if Q needs an element of A mod G, the initial value, would be infinite.
I'm not thinking of it as initial value. So I'm thinking of it as just as a lemma by itself, and then I'm using it.
As the path, you're thinking of it as the whole path.
So I'm thinking of okay. So first of all, if you assume this part, the main step, then what you have from this condition here, you have that for each t, xn of t is a tight family of a/g valued random variables. So you have xn t is a tight family, okay, for each positive t. And then you can extend it to show that for any t1, t2, tk, xn t1 to xn tk is a tight family of k tuples of and so then using the continuity, then use a diagonal argument to get your all finite dimensional distributions of your subsequential limit measure.
I see. That's very nice.
Oh, thank you.
Okay. Are there other questions?
Let's see, would it be too difficult to sketch how you make the estimates for U of 1? You're making the lattice approximation, you're making the approximation by using Fourier series.
Fourier series, yeah. So Fourier series.
So you have to show that SYM for a fixed Fourier cutoff remains bounded as you remove the cutoff, but for a positive t.
Yes.
Is that right? Okay.
Yes. So for U1 theory, you can actually explicitly write down everything. You can explicitly write down the all required quantities, because you have a way of writing down the random variable itself with the cutoff. After the cutoff, you can write down using Fourier series and Gaussian random variables, Gaussian coefficients. You can write it down, and then from that you can compute the Yang-Mills action, and then you can explicitly show that sequence of random variables is a tight family. So
I see.
Yeah.
Okay. Well, if there are no other questions, then let us thank Sourav again.
Thank you.
Okay.
I'll stop the recording, but we can have some informal discussion if people